next test is field test of DC motor. So why the series motor is not operated under no load condition? So we know the formula. EB is directly proportional to N into 5. N is directly proportional to EB by 5. For a DC series motor, the flux is directly proportional to armature current. Then speed is inversely proportional to armature current. Under lightly loaded condition, IA is very small. So if IA is minimum, the speed will be dangerously high. Speed is dangerously high. So that's why the DC series motor can never be started under no load condition. The brake test on DC shunt motor are for smaller machines. We can apply brake test. For large machines of a DC series motor, for large DC series motors, we can apply the field test. And this is not, brake test is not suitable for large DC series motors. The brake test, when you are conducting a brake test, the motor should never be started under no load condition. The minimum load you have to kept on the shaft of a DC series motor. If the Simmons test is not suitable for DC series motor, and Hopkins test is also not suitable for DC series motor, and we should conduct a special test that is called the field test of a DC motor. Here, this is a DC series motor. The motor series field winding is connected in series with the motor, and the generator field is also connected in series with this machine, that is called the motor combination. Why? Because in order to calculate the iron losses for both the machines is same. In order to calculate the iron losses, we are separately excited DC series generator are used. Here we are using a two machines, and one is called the motor and another one is generator, and the generator field is separately excited, and that is in series with the motor combination, that is called the armature as well as the series field. This is our supply voltage. The current drawn from the supply is I1, and the voltage which is applied across the motor is V1. Okay, and the current which is delivered by the armature is I2, and the load voltage, the across load, we are connecting on voltmeter. This voltmeter indicates the V2, that is called the terminal potential difference of generator. Okay, and one machine acts as a motor and another one is acts as a generator, and both are series machines only, and the series motor is coupled to now series generator. The resistance R is changed until this I1 current shows full load rated current, that is mentioned on nameplate details of DC series motor. And if it is a rated current, means I2 is also rated. The power taken from the supply, see, power taken from the supply is equal to V into I1. Yes, V into I1. So V1 is equal to, yes, this is a V and I1. And output obtained from generator is V2 into I2, If you want to calculate the total losses in a machine, which is very simple total losses in a machine, in a machines, total losses is equal to input power is V1 I1 minus V2 I2, that is VI1 minus V2 into I2. That is called the total losses. And if you calculate the armature copper losses, armature copper and field copper losses, WC is equal to, see, armature copper loss is Ia square RA, armature copper loss is Ia square into RA for a motor. And one more copper loss is there, that is called the series field copper losses, that is Ia square into RSC. So how many windings are there? Series field windings. This is for generator and this is for the motor. So that's why this resistance is RSC and this resistance is also RSC. Then Ia square into 2 RSC. 2 RSC. Now the copper losses is equal to RA plus 2 into RSC whole square into, that is I square R, right? I square R, right? I1 square into RA plus 2 RSC plus field copper losses are I2 square into RA. I2 square into RA. So this is current which is delivered from the armature, and the generator is also having a resistance RA from the generator side, that is I2 square into RA. If you want to find out the total stray losses, from the total losses, if you subtract the armature copper and field copper losses, then I will get the total stray losses. For stray losses per machine, so I have calculated for 2 machines. For one machine, that is total stray losses divided by 2. So this is WS. If it is a motor, again the same story is repeated. The input power is equal to V into I1. From this you can subtract the total losses. Yes, total losses is equal to armature copper loss plus field copper loss plus stray loss. This is I1 square into RA plus RSC, and this should be equal to, yes, I1 square into RA plus RSC field copper losses these two losses plus stray losses. Then you can find the output of the motor, input minus losses. Output of the motor is equal to input power minus losses. The input power is V into I1 minus I1 square into RA plus RSC plus WS minus of. Then I can calculate the efficiency of motor, output power divided by input power multiplied with 100. The input power is V into I1 minus I1 square into RA plus RSC plus WS divided by V into I1 multiplied with 100. Then I got the efficiency of a motor. If it is a generator, for a generator output power is, output of the generator is V2 into I2. And the field copper loss of generator is I1 square into RSC. Why? Because it is separately excited. You can check it. The current which is flowing through RSC of a generator is I1. And after that, armature copper loss. The armature copper loss is equal to I2 square into RA, add total losses. Anyway, we are having a stray losses also. Armature copper loss plus field copper loss plus stray losses. I1 square into RS, I2 square into RA plus I1 square into RSC plus stray losses. Then you can calculate the input power is equal to V2 I2 output power plus total losses for generator. Okay. Then efficiency of generator is equal to output power divided by input power into 100. So output power is V2 I2 divided by V2 I2 plus I2 square RA plus I1 square into RSC plus WS into 100. This is called the efficiency of generator of a field test. So first of all, for optimization test and this test also we are calculating the stray losses for each machines. After that we are calculating efficiency. So if you draw the curve between efficiency versus load current, the curve will be like this. So this is called the maximum efficiency. Maximum efficiency. So this is at okay, at this we are observe that variable losses is equal to constant losses. This is a full load current. The efficiency is also full load. Okay. Coming to the problem on field test on DC series machines. So this is our question. A field test on two mechanically coupled similar motors with their fields are connected in series. Two mechanically coupled similar machines. This is not motors. One machine acts as a motor and another one acts as a generator. And with one machine running as a motor and another as a generator, the armature current of the motor is 40 amperes. Yes, line current and armature current and the series field current all are same. The armature voltage, yes, the voltage across this combination is 200 volts. The drop across its field winding is 15 volts. So the field winding of a generator, this one is field winding of generator, and that too it is separately excited DC generator. The resistance of each machine is 0.4 ohms, and the calculate the efficiency of each machine at this load. Okay, so I1 is a motor input current as 40 amperes, 200 volts voltage across the armature, and I2 is a load current 32 amperes. V2 is a voltage across the generator is 160. So this is called the V2, and this one is I2. So then I calculate the output of the generator is V2 into I2, that is 160 into 32. So then I calculate the output of the generator is 160 into 32, 5120 watts, and the input of the motor is you can check it, 200 into 200 plus, because the voltage across this combination, this is 200 and plus 15. If you apply the KVL to this loop, let us find the supply voltage is V. So minus V plus 200 plus 15 is equal to 0. Then V is equal to 215 volts. Our supply voltage is 215 volts. And 215 into 40, 8600 watts. If the input minus output will gives the total losses of two machines, input minus output power, that is 3480 watts. The series field resistance is not given. Then you should find out the series field resistance. How means the current which is flowing through series field winding is 40 amperes, and the voltage which is applied across the series field winding is 15. Then I should calculate the RSC is equal to V divided by current. So V is 15 volts across the field winding divided by 40. Then I got the RSC value. Okay, so if you calculate the RSC for motor and generator, both are same. If you want to calculate the total copper losses, the same formula you can use it. Series field winding as of a motor consists of RSC and the generator consists of RSC, and the motor armature resistance is RA. Now RA plus 2 RSC into the current which is flowing through the motor is I1 square, plus armature copper losses of the generator is I2 square RA. Then I got the total losses. If I want to calculate the stray losses of the set, total losses, from the total losses we should calculate the we should subtract the total copper loss. Then I got the stray losses for set. The stray losses for each machine is total stray losses divided by 2. That should be equal to 1230.4 divided by 2. Then I got the answer is 615.2. Again, individually you can add. The motor input is V into I, 200 into 40, 8000 volts. The armature copper losses is IA square into RA plus RSC for a motor. Calculate this, and stray losses we are already calculated. You should find out the total losses, and this total losses is subtracted from the motor input from the DC from 8000. Then you will get the motor output. So output power divided by input power will use the efficiency. The motor efficiency will be 76.81. If it is a generator, the armature copper loss is I2 square into RA, and the series field copper losses is V into I, that is 15 into 40, that should be equal to 600 watts. Then the stray losses we are already calculated, add that. Then output of the generator is V to I2, V to I into I2, so output plus losses. Then efficiency of generator is calculated, output power by output power plus losses. The power losses will be added for output of a generator, losses will be subtracted from the input of a motor. Then I got the efficiency is 76.26.